You have a process without a thread.
Maybe.
Remember the definition of the process. What was the definition of the process? Process is a program in execution, right? So the process has two parts, okay? It has two functions. One is the resource grouping, okay? Grouping of all the data that is required by the process. What is the data? The stack, the address space, the virtual tables, virtual memory tables, and the cache information, all the registers, etc. These are all the data for a process to run. And the process has another part, it is the execution, okay? So each process has to have a single execution, at least one execution, okay? That execution part is called a thread, okay? So each process has to have at least one thread. If you have more than one thread, then we have a parallelism structure like this. So this is one way of achieving parallelism, okay? Achieve parallelism by these executions, parallel executions with three different processes, or you can have many threads in a single process. So that means that you cannot have a thread without a process, and the other way too, you cannot have a process without any threads. You need to have at least one thread inside, because thread is the execution part of the process. That's the idea. Why don't we have more than one execution inside a process? So people are saying that, okay, these are the processes and the threads. When do we implement these thread libraries? Remember the POSIX thread library? It is the create process, terminate process, or yield the CPU, or join the process, etc. You have more than 100 functions like these for the processes. Where should we implement all these functions? Should we implement them in the kernel space or in the user space? This picture is implementing the process threads in the user space. This is for the threads implemented in the kernel space. We will look at this one first. So when you are implementing the threads in the user space, you put all of your thread-related data inside the process. Okay? The process keeps all the thread-related data. What is the thread-related data? What do we keep in the thread? It's called thread table. What do we keep in the thread table again?
Thread ID, process name.
Thread ID. What else?
Datas, all the values.
Required like the registers and the program counter. Program counter is something we require, right? And the registers, right? And the stack information. All the rest. See, this table is important. These have to be kept for each thread. So I need to put them in those thread tables. All these information, okay? All this information has to exist for a single process, okay? So I don't need to keep this information. I don't need to keep this information for the threads per thread item. So I need to keep all that information in the user space and inside the process actually. The process handles everything. So for each process, they repeat this data. Okay. So this is how we implement the processes in the user space. Thread creation, destruction, and scheduling done at the user level, including the scheduling. Which thread is going to work, which thread is going to sleep, which threads are blocked. They are all managed in the user space without any kernel help. Okay. To create in the user space, okay, you must allocate storage for stack, program counter, registers, state, etc. in a thread table. This is where you keep your thread table in the user space. Okay, and when a thread yields the CPU, what does this mean? Thread yields the CPU. It's a term. What do you understand from this term? A thread yielding the CPU.
Lets another thread to use the CPU.
It lets another böyle İngilizce konuşuyor da niye konuşmadın şu ana kadar? It lets the bunu Türkçe söylemem lazım böyle. O vurguyu incele yapamıyorsunuz. It lets the CPU use the CPU time while it is running. Even though it can continue, it yields the CPU, or it blocks. In that case, it has to block because it needs something from the operating system or some I/O device. Okay. When a thread yields the CPU or blocks, the thread library saves everything in the thread table, not the kernel space, not the hardware. The thread library does this stuff. Okay. It's like you're writing the code yourself. Okay. And the thread scheduler finds the highest priority thread that's ready to run. There might be more than one thread ready to run, and the thread scheduler finds the highest priority one, usually depending on the history. Okay, and its registers, counters, etc. are restored from its thread table. So thread table is very similar to what? Thread table is similar to process table. Yeah, process table is managed by the kernel. In this case, the thread table is managed by the libraries running in the user space. So let's look at some of the advantages and disadvantages of the user level threads. First, efficiency gain. Okay, you don't need to make any system calls, right? Because everything is in the user space. No user calls. No system calls means that it is efficiency, right? Because making a system call is inefficient sometimes. Because when you make the system call, you need to save. It is like making a function call, right? You need to save lots of data. You need to let the system run for a while, and you are yielding the CPU actually when you are making the system call. So your program will suffer from some inefficiency. Okay. No context switch. What is a context switch? We talked a little bit about context switch, but you should know this from the organization's lectures, right? Context switch. It's like process switch, but what happens when you do the context switch?
Diğer prosese geçmeden önce bilgileri kaydediyor. Daha sonra geri döndüğünde...
When you are switching between the processes, okay, you need to save all the process states and everything, all the data in the process table, right? And you are switching to something else in the kernel mode, and kernel mode is a different environment. So no context switch means that I am not running into these kind of inefficiencies. We will talk about the context switches later. Okay. So it is done by the help of the hardware, but it is still a very expensive process. No copying data safely across the production boundary. I mean, when you make a system call, you need to copy data from your user space to kernel space. So data safety boundary, you need to copy data. So kernels has to be careful about this kind of copying. It might cause some problems, and there might be some security checks, which means inefficiency again, and no need for to flash the hardware memory cache. Since you are going into the kernel mode, your cache structure will all change. That will hit you a second time in terms of the efficiency, because your memory cache will be invalidated because a new world is starting now. So these are all the plus sides of the implementing threads in the user space. Other advantages: I can have my own scheduler, thread scheduler. Okay, I don't have to depend on the operating system scheduler. I can have my own scheduler. For example, I can write my garbage collector as a thread, and I will let it run from time to time, but it is in my control, right? It is not in somebody else's control. I can manage this kind of stuff in a very, very efficient way because I have my own scheduler. And it scales better than the kernel level threads because I am not depending on the kernel. I am not using any kernel level resources. Everything is in my hands. I can make it efficient. I can keep my stacks myself, and I can do all kind of optimization in terms of better code, efficient code, and better usage of the space. So these are all advantages because everything is in my hand. It's like writing a program in C, right? nobody restricts you, so you can write very efficient code. You can optimize the CPU time, you can optimize the memory used, you can use all kind of tricks. But there are problems. What kind of problems we have? Can you think of any problems implementing the threads in the user space? What are the problems? I mean, if we didn't have any problems, then that meant that everybody chooses this type of alternative. They don't use any kernel level threads. But there are some problems with the user level threads. What are the problems? Tell me a few problems. What would be the problem implementing these in the user level? Let's say I have a process and 3 threads are running, okay, and they are running all in the user space, right? So these are user space threads. This is my kernel. Let's say one of them, yes.
Do I have to give any information about the scheduling of the threads when we create the thread? Is it necessary?
You mean you don't
it's
use
necessary because I think
you need to have all that information, but you don't have to report that information to anybody else because they are all happening inside your thread, inside your process.
if we give that information, for example, we can match the scheduling of the threads.
We can what? We can what?
Demonstrate the time schedules of the threads. For example, we can give a highest priority for our threads,
Yes.
but some other threads affect negatively.
But you are writing all of your threads yourself. I mean, this is your thread, this is your thread, and this is your thread.
Yeah.
You are doing your scheduling between these 3 yourself. If there is another, let's say, if there is another process and it has its own threads, this thread cannot interfere with this thread. They are because they are at different processes. So there is no security problem between those threads. The problem are between these 3, and these are written by the same programmer, and they are working towards the same purpose. Okay. Yes.
Hocam bir thread hani böyle çalışırsa içinde bir interrupt falan yoksa başka bir thread de onun çalıştığı şeyi kullanmak istiyorsa o sorun olabilir belki. Hani biz de onu kontrol etmemiz gerekiyor ya.
Aynı
İnterrupt yoksa derken?
Mesela bir thread var, bir tane değişkeni kullanıyor. Başka
Evet.
bir thread de o değişkeni kullanmak istiyor.
Evet.
O thread eğer ona izin vermezse, hani ben ona izin vermezsem sorumluluk bende ya.
Evet.
Diğer thread de onu kullanamaz. İşte orada bir sorun olabilir.
Ama onu user level olmasında bir dezavantajı yok ki. Aynısını kernel level'de de yaşayabilirsin. Kernel level'da o zaman nasıl çözeceksin o problemi?
İşte o arka planda düzeltir diye düşünüyorum.
Yok, onu da birilerinin çözmesi lazım. Yani onun kernel level'da da aynı problem var. Aynı işkenceyi orada da çekeceksin. Evet.
If this process blocks because of an I/O input,
Yes.
then all threads may
Yes.
stop.
That's exactly the point. If this thread needs some kind of an I/O, it asks the operating system to do the I/O, right? And the operating system blocks the whole process, right? It blocks the whole process. So while the other 2 threads can continue, they cannot in this case because operating system keeps this process in the blocked state, even though these 2 threads can continue. So because the operating system doesn't know about the threads in this case, thread library is implemented in the user space, operating system thinks that a regular single-threaded process is running, right? So if a thread blocks, it blocks the whole process. That means that all of your threads are... So why are we doing the multi-threading? We are doing it for the better utilization of the CPU, or we are using it for the convenience writing in an application level program like the word processors. In this case, when the word process is writing to the disk, updating of the screen, or taking the input from the keyboard will be blocked too. That's something bad. So getting help from the operating system is important. In this case, while we are trying to get the help from the operating system, it is working against us. That's one of the problems with the user level threads. Blocking system calls is the main problem. Page faults. We don't know about the page faults yet. We didn't talk about them yet. Okay, but pages are memory sections. Okay, when you are using virtual memory, when you don't have enough memory for all the programs to run, you write some of the programs to the disk. They stay on the disk. They are not on the memory. When needed, they are immediately loaded from the disk to the memory. Okay, from the disk to the memory. So these are called page faults. If something is missing from the memory, then a special hardware routine, hardware plus operating system routine runs, and it loads them from the memory to the from the disk to the memory. If one of the threads causes a page fault, okay, it has to wait until the pages is loaded, but the other threads can continue because they have their own instructions and their memory are okay. Okay, in this case, like a blocking system call, one of them causes the page fault, the others can continue. In this case, they will not continue because the operating system thinks that there is a single thread running inside the process. Another one is this: enable it to benefit from multiprocessor CPUs. You can explain this to me. It is, you can guess why. If you are implementing your threads at the user level, not the kernel level, then it will be difficult to benefit from the multiple CPUs. Why?
Because threads, some resources allocated on some CPU's cache, but not other CPU's core cache. So when one core is running this process, others can't run because they don't have their cache. And
you are saying that it's a cache related, so it's an efficiency issue. Is that? It doesn't say it is an efficiency. It says that you may not. You have 3 threads running in parallel, and you have 3 CPUs. If you implemented the thread library at the user space, you cannot benefit from all of these CPUs. You need to run all of your threads on a single CPU because CPU scheduling is done by who? By the operating system, right? By the kernel. But the kernel doesn't know that you are running 3 threads. Okay? It thinks that you are running a single thread, so the CPU assigns only one processor for you, even though 2 of the processors are sitting idle at the user level. You need to run your threads on the same CPU, which is inefficient in terms of reusing the system resources. Okay, and the kernels can automatically grow per thread stacks. I mean, each thread has its own stack, right? And growing this stack, or when you don't need it, shrinking it, is done by the kernel at the process level. But since we implemented our threads at the user level, the operating system cannot help us to grow the stacks and shrink the stacks. We need to do all of these. With our code. We cannot benefit from them. We cannot benefit from the operating system procedures to growing the stacks, which causes some inefficiency. Okay.
Could you please explain the third one more time?
The CPUs.
No.
CPU allocation is done by the operating system, right? This is one process. This is one process. Operating system says that. Operating system doesn't know there are 3 threads inside it. Doesn't know there are 3 threads inside this. So it says that, okay, this is your CPU and this is your CPU. You will run on this one and you will run on this one, right? That's what it can do at best. Okay, it assigns CPUs to threads, or CPUs to processes, or processes to CPUs. Suppose I don't have this process and I have another CPU, 3 CPUs. Since operating system thinks that there is a single thread inside this process, it designs a single CPU for this process. So 2 of these CPUs are sitting idle. They are not doing anything. Okay? They are not doing anything. That's inefficiency. Even though I can run each of those threads on one of these CPUs, I can't do it because I don't get the help from the operating system. Operating system doesn't know that I am running threads. So these are the downsides. So these are the downsides of having the user level threads. Okay, this is an explanation about the growing the stack. Again, the fourth item in the previous, this one. Okay, the system allocates certain amount of memory for an initial piece of stack for each process, and references to other potential parts of the stack cause a trap. In this case, the stack is growing, and I am using too much memory for the stack, and this trap looks like an attempt to use an unallocated space. So the kernel allocates more space for the stack and extends it. It does it automatically using sophisticated algorithms. But this only works if the kernel knows where the stack is, and it only works for a single stack for the whole process, because the kernel does not know we have more than one thread. Okay. Again, building blocking system causes the problem. When you say call this routine read, and there is no data available, then the whole thing blocks, and it causes inefficiency. Even though other threads can continue, I cannot continue. Okay, this is contrary to the purpose of having threads. Difficulty issue is the user level threads need modification. Okay, in order to deal with this problem at the user space, you need to make modifications for those operating systems so that your calls to the operating system does not block. Okay, it does not block.